Rigorous analysis of SBSA Hypercube capacity with quantized dimensions. Aaron Cattell. June 22, 2025. Abstract. We present a rigorous mathematical analysis of the size-based slot allocation, SBSA, Hypercube model, addressing the practical implementation challenges of previous theoretical treatments. While earlier work claimed uncountable infinite capacity through continuous parameters, we demonstrate that real-world implementations require discrete, bounded dimensions. Our analysis introduces a quantization framework that transforms the theoretical continuous width space into a finite, computable domain while preserving the system's core advantage of O(1) file operations. We formally prove that the quantized SBSA Hypercube system achieves an exact capacity of 1.599840080008 by 1016 addressable locations across 4 dimensions: size classes, quantized thickness, quantized width, and version indices. This represents a practical capacity of approximately 16 petabytes of addressable space, while maintaining deterministic constant time performance guarantees. Our main contributions include 1. A constructive proof of system capacity with explicit bounds. 2. Rigorous analysis of the quantization function's injectivity properties. 3. Computational complexity guarantees for all operations. 4. Practical storage efficiency bounds. And 5. Empirical validation through performance benchmarking and space utilization analysis. Unlike previous theoretical models involving uncountable infinities, our framework provides implementable solutions with precise mathematical foundations and demonstrated performance advantages. The results demonstrate that quantized SBSA systems can achieve massive scalability, 1016 locations, with guaranteed O(1) performance, making them suitable for large-scale distributed storage applications. Experimental validation confirms theoretical predictions, showing consistent sub-5 ms retrieval times regardless of system size, compared to linearly degrading performance in traditional flat storage approaches. Introduction. We present a rigorous mathematical analysis of the size-based slot allocation, SBSA, Hypercube model with quantized dimensions, providing exact capacity bounds and computational complexity guarantees for the practical implementation. This work addresses critical gaps in previous theoretical treatments that claimed uncountable infinite capacity while ignoring fundamental implementation constraints. 1. Mathematical framework. Definition 1. SBSA Hypercube space. Let the SBSA Hypercube space be defined as the 4-dimensional Cartesian product H equals S times T times W times V, where equals at S0, S1, S2, S3 are size classes, equals a 0, T, 2T, Tmax a quantized thickness, equals a WM, WM plus W, WM, a quantized width, equals a 0, 1, 2, Vmax a version indices. Definition 2. Quantization parameters. The quantization parameters are defined as WM equals 0.01, WM equals 106, W equals 0.05. Tmax equals 106, T equals 5. Vmax equals 104. 1, 2, 3, 4, 5, 6, 7, 8. Definition 3. Quantization function. The quantization function Q, R times R plus R is defined as Q, x, delta, equals delta times x. Delta plus 1, 2. Where times is the floor function. Main results. 9. Lemma 1. Cardinality of quantized dimensions. The cardinalities of the individual dimension sets are S equals 4, T equals to max, T plus 1 is equal to 200,001, W equals WM, W V equals max plus 1 is equal to 10,001, 10, 11 plus 1 is equal to 19,999,981, 12, 13. Proof. 4s. Direct counting of size classes are 1 kilobyte, 2 kilobytes, 4 kilobytes, 8 kilobytes. 4t. The thickness values form an arithmetic sequence as 0, 5, 10, 106. The number of terms is 1060. 5 plus 1 is equal to 200,001. 4w. The width values form an arithmetic sequence to 0.01, 0.06, 0.11, 106. The number of terms is 1060.01. 0.05 plus 1 is equal to 19,999,981. 4v. Direct counting of integers is 0, 1, 2, 104. It gives 10,001 elements. Theorem 1, SBSA Hypercube capacity. The total capacity of the SBSA Hypercube system is exactly H equals S times T times W times V equals 1.599, 984, 008, 008 times 1016. 14. 2. Proof. Since S, T, W, and V are finite sets, and the mapping function f, hs times T times W times V defined by f of S, T, W, V equals S, Q, T, T, Q, W, W, V is surjective by construction, we have H equals S times T times W times V equals S times T times W times V equals 4 times 200, 001 times 19, 999, 981 times 10, 001 equals 1.599, 984, 008, 008 times 1016. 15. 16. 17. 18. Corollary 1, computational complexity. The mapping function f, hs times t times w times v has computational complexity O, 1, 4. Element insertion. Element lookup. Element deletion. Proof. Each coordinate computation involves size class lookup, O1, hash table access. Quantization operations, O1, arithmetic operations, division, floor, multiplication. Bounds checking, O1, comparison operations. Since all operations are constant time and independent of system size, the total complexity is O1. Theorem 2, injectivity of practical mapping. The mapping function G, valid inputs H defined by G S T W V equals S Q T T Q W W V is injective on the domain of quantized inputs. Proof. Suppose G S1 T1 W1 V1 equals G S2 T2 W2 V2 for valid inputs. Then S1 Q T1 T Q W1 W V1 equals S2 Q, T2, T, Q, W2, W, V2. This implies S1 equals S2. Q, T1, T, equals Q, T2, T. Q, W1, W, equals Q, W2, W. V1 equals V2. 19, 20, 21, 22, 23, 24. Since inputs are already quantized, Q, T1, T, equals T1 and Q, W1, W, equals W1. Therefore, S1, T1, W1, V1, equals S2, T2, W2, V2, proving injectivity. 3. Experimental validation. To validate our theoretical results, we implemented the SBSA Hypercube system and conducted comprehensive performance analysis. This section presents empirical evidence supporting our mathematical claims. 4.1 Hypercube Space Utilization Analysis. Figure 1 demonstrates the practical distribution of files across the SBSA Hypercube space. The visualization shows a 3D projection of the 4-dimensional hypercube, with the 4th dimension version represented by color coding. Figure 1, SBSA Hypercube projection, showing 4D SBSA cube groups. The plot demonstrates uniform distribution of files across size classes, x-axis, thickness, y-axis, width, z-axis, with version dimension encoded in color. Each point represents an active file location in the hypercube space, validating the theoretical uniform distribution assumptions. Key observations from the hypercube analysis. Uniform distribution. Files are distributed across all 4 dimensions without clustering artifacts. 4. Quantization validation. Discrete points are clearly visible, confirming proper quantization implementation. Space utilization. The system effectively utilizes the theoretical address space. No hotspots. No obvious concentration of files in specific regions of the hypercube. 4.2 Performance benchmarking. Figure 2 presents empirical timing results comparing SBSA Hypercube performance against traditional flat log memory structures. The benchmark measures retrieval times across varying system sizes to validate our O1 complexity claims. Figure 2. Performance benchmark comparing SBSA Hypercube vs flat log memory. The SBSA system maintains constant retrieval time, 0.004 s, regardless of system size, while flat log performance degrades linearly. At 10,000 entries, SBSA achieves 4.5 times better performance, with the advantage increasing at scale. The benchmark results provide strong empirical support for our theoretical claims. Constant time performance. SBSA retrieval time remains stable at 0.004 s across all tested system sizes. Scalability advantage. Performance gap widens with system size, reaching 4.5 times improvement at 10,000 entries. O1 validation. The flat performance curve confirms theoretical O1 complexity predictions. Practical superiority. Demonstrates clear advantages over traditional approaches in real-world scenarios. 5. 4.3 Statistical analysis of results. The experimental data supports the following quantitative conclusions. Theorem 3, Empirical performance bounds. For SBSA Hypercube systems with n less than or equal to 104 entries, the retrieval time T(n) satisfies. T(n) equals 0.004 plus or minus 0.0005 seconds. With 95% confidence, confirming theoretical O1 complexity bounds. Practical implications. 25. Theorem 4, storage efficiency bound. If each hypercube coordinate requires c bytes of storage, then the theoretical maximum storage requirement is bounded by storage less than or equal to c times 1.6 times 1016 bytes equals 16 c petabytes. 26. Corollary 2, scalability analysis. The system provides deterministic O1 performance while supporting a practical capacity of approximately 1.6 by 1016 distinct file locations, making it suitable for large-scale distributed storage systems. Related work and comparison. Traditional file systems rely on tree-based structures, B-trees, AVL trees, or hash tables with collision resolution. Our empirical results demonstrate that SBSA's pre-allocated slot approach eliminates the comparison bottleneck inherent in tree traversal, achieving superior constant-time performance. The quantization framework presented here bridges the gap between theoretical infinite capacity models and practical finite implementations, providing a constructive approach to achieving massive scalability with deterministic performance guarantees. Conclusion. This analysis provides a rigorous mathematical foundation for the SBSA Hypercube model with quantized dimensions, supported by comprehensive empirical validation. Unlike previous theoretical treatments involving incountable infinities, this practical implementation offers exact capacity bounds, 1.6 by 1016 addressable locations, guaranteed computational complexity, O1 operations with empirical validation, constructive proof, the system can actually be implemented and deployed, practical scalability, sufficient capacity for real-world applications, performance superiority, 4.5 times improvement over traditional approaches at scale. 6. The quantization approach resolves the theoretical impossibilities of the continuous model while maintaining the core advantages of constant-time file operations and massive scalability. The experimental validation confirms that theoretical predictions translate directly into practical performance gains, making this approach suitable for next-generation distributed storage systems. Future work should investigate concurrent access patterns, memory hierarchy effects, and integration with existing distributed file system architectures to further validate the approach at enterprise scale. 7.